Okay, last time we ended over here that some materials offer more resistance to the flow of electricity than others. The reason is electrons do not swim in a conductor. For example, if one electron is pushed in, all the electrons of the conductor that are in that particular conductor are pushed forward. The last electron goes into the appliance. Appliance is also a conductor. The electrons flow in the appliance. At the same time, last electron of the appliance goes into the neutral wire, and then it comes back to the battery. So the time the battery pushes one electron out, one electron is pushed back into the battery from the other terminal. The difference is the electron that leaves the battery has more energy. The one that is coming back into the battery has low energy. All that battery is supposed to provide in a circuit is not current actually. It is energy. When we say a battery is drained out, it does not mean it now has a lack of electrons. It never had any extra electrons. It only had energy that it could transferred or installed on the electrons, which could move in the conductor and transfer energy to the other appliances in the circuit. Now, all the electrons have to participate, and this to a point where we need to understand that electrons do not have to swim in a conductor; they actually have to drift. This is an example where people are sitting on a bench, and if one person wants to sit on it, one extra person wants to come on, there's no more room. So when he pushes everybody forward, the last person falls. In some cases, this game will be very easy. If those people are wearing soft or slippery pants and they're sitting on a slippery bench, this game will be very easy to play. But if they wear rough clothes and they are sitting on concrete rough bench, this game will be very difficult to play. And if there is an armrest on any end of the bench, even if the armrest is in the middle of the bench, this game will become near impossible to play. Okay, so when we say some material has more resistance, it actually means that uh, that particular material offers more opposite force to the electrons when they attempt to slip, when they attempt to drift. Some materials offer less resistance. So nature of material means resistance depends on different things. One of them was nature of material. Nature of material is either resistivity or the number density. What is meant by resistivity? Resistivity means that if we decide for a fixed size of a conductor, like a conductor is 1 meter long, 1 meter wide, 1 meter high, and if we allow the electricity to flow, how much resistance will that conductor offer? Like we have to fix the size, and we will be making those conductors with different materials. All of them will have same size, and then we will say which one is offering more resistance. So resistivity is specific resistance. Specific resistance means resistance of a conductor that has specific sizes. For example, its area should be 1. Its length should also be 1. And whatever resistance that is offered by a conductor of cross-sectional area 1 meter square and length 1 meter is known as resistivity of that material. Let me write this over here. Here is an extra note. Resistance of a conductor that has cross-sectional area of 1 meter square and is 1 meter long is called resistance of, sorry, not resistance, resistivity of the material of the conductor. Resistance belongs to a particular resistor and resistivity belongs to a material. It is a kind of specific resistance. Resistance depends on number density as well. What is number density? Number density is also known as charge density. It means how many free electrons. By term free electrons, I mean flippable electrons. Free electrons means easy to slip electron. So metals have excess of these easy to slip electrons. That's why metals are good conductors. And non-metals, they don't have so many slippable electrons. That's why we don't say they have. One more thing, be very careful. I think I mentioned that in the previous class as well. Do not think free electrons mean extra electron. Free electron means electrons that can easily slip. Okay? Electrons that can easily slip. Now, what else resistance depends on? Did you say something? Did anybody say? Okay.
No.
Now, the length of a conductor also affects resistance. If you have a longer conductor, you will have more resistance. This is why if you have an extension cord or extension cable which has a very long cable, sometimes we use these kind of cables to uh, put a light in a lawn or some outside function or something, and we need electricity to be taken from inside of house to somewhere outside, and we use a very long cord. The problem that we have in that kind of transfer of electricity is that because of the length of the cord, we don't get as many volts at the end of that long wire, because in the long wires, although they are made of very good material, but when they have more length, they have more resistance, and that's why they consume more energy. Now, cross-sectional area. If a conductor has a bigger area, it will have smaller resistance. And if a conductor has smaller area, it will have more resistance. Area and resistance are inversely proportional. This is why if you are using if you need to have a wire that allows small amount of current, and you want to use it for an energy saver or a mobile charger, you like things that do not require a huge amount of current. So what happens is you use thin wires for them, because you know that I have to transfer smaller amount of current, so I can do it with a wire that uh, that allows small amount of current, and the wire that allows small amount of current, it means have more resistance. Similarly, if you are installing something which requires more energy, like an air conditioner or a refrigerator or electric stove or washing machine, things that consume more electricity, you need to provide them with more electricity. So what you give them, or you install them with thicker wires, thicker copper wires. Why? Because thick wires will have smaller resistance, so they will offer small resistance to the flow of current, and more current will easily flow through the wire. So cross-sectional area affects size of resistance. Now, one more problem that normally students have. When I ask them the area of circle normally is A equals to pi r square. But this is for math only. Problem is when you go to the lab and measure diameter, you cannot measure radius. You always go in the lab and measure diameter. For example, if you use a micrometer, what you will measure for this wire? Diameter. Use vernier caliper, diameter. There is no way, no device that can directly measure radius. So we go and we measure diameter. So we use diameter formula. Now, some of you might now think that, okay, if we measure diameter, but be a smart person and just half it, you will have radius, and then you use that radius. That should come to your mind. But there is another problem. The first topic that we studied in physics, AS, was errors and uncertainties. Every measurement that we make with any instrument, it comes with a very specific uncertainty. And when we double something, half something, square something, divide something, multiply something, add or subtract or do anything, the problem is that error is also multiplied, add, subtract, ratioed, and multiple things happens to the errors as well. So messing up with the value that we have measured is not an easier thing. So we prefer the value that we have directly measured. In that case, that will come with its own uncertainty and we can deal with it. Okay. So what is the formula of area of circle in terms of diameter? Area of circle in terms of diameter is pi d square by 4. Pi d square by 4. So this is the formula that we will use here. Okay. So as radius is resistance is inversely proportional to area, and area is pi d square over 4. So it means resistance is inversely proportional to 1 over pi d square over 4, which can be reduced to resistance is inversely proportional to or directly proportional to 4 over pi d square. That means resistance is inversely proportional to d square. This is very important. So if this means that if you double the diameter, you use a wire that has double diameter, it means that wire will have half the resistance. Oh no, we are missing something. If we double the diameter, resistance will be quartered. Resistance will be quartered. If you triple the diameter, resistance will reduce by 9 times. Similarly, if you half the diameter, resistance will be quadrupled. It will increase to 4 times. So resistance and diameter have inverse square relationship. Now, last thing that affects the size of the resistance, it is temperature. Now, temperature affects resistance differently for a normal conductor and for a thermistor. Resistance is affected because of temperature. Remember, temperature can increase or decrease resistance. It can do both actually. So if we increase temperature of an ordinary metal conductor, what will happen? Metal conductor electrons will like particles will start vibrating with more kinetic energy. They were already vibrating, but now because of the high temperature, they will vibrate with more kinetic energy. Lattice movement will increase. It will become difficult for electrons to drift. So for an ordinary conductor, ordinary metal conductor, when you increase the temperature, resistance of the conductor increases. With the increase in temperature, resistance of the conductor increases. Here we have this graph. This is the current against volt graph. I have drawn two different graphs. One is in the blue line, one is with the red line. The one with the blue line is known as ohmic conductor. An ohmic conductor means a conductor that obeys Ohm's law. Ohm's law is that current and voltage are directly proportional to one another. On the other side, non-ohmic conductor. Non-ohmic conductor is a conductor that does not obey Ohm's law. For example, filament lamp. And the reason is not it is not obeying Ohm's law. The reason is that there is a condition where Ohm's law is not applied. Ohm's law is only applied if temperature is same, if temperature is not increasing. But for a filament lamp, I hope some of you might know, because it is something that is getting very rare these days. Now we have energy savers that produce white light, but in old days there were filament lamps. They were used to produce that yellow glow, and that was because a tungsten filament, when current passes through that tungsten filament, it becomes very hot. Its temperature increases to about 2900 to 3000 degrees Celsius, and it becomes visibly hot. Now, because it becomes visibly hot, it means its resistance should increase. And I hope you can see that red line over there. The red line, if it would have continued its original or initial pattern, the current should have increased like this. But it did not. Why? Because when the current increased, voltage increased, energy was consumed inside the filament lamp, the temperature of the filament lamp increased, so resistance of that filament lamp increased as well. With the increase of temperature, resistance has also increased. So current could not increase as much it should have for the corresponding increase in voltage. This is because of increase in resistance of an ordinary conductor when temperature increases. Now, let's discuss this one. What is this? This is a semiconductor thermistor. Semiconductors, they are between conductors and non-conductors. And why we say they are between, it is not because they have a mediocre resistance. No. Get this thing very clear in your head. A semiconductor is a conductor that has a resistance that can change because of the change of the physical condition around the conductor. Some conductors, their resistance depends on the direction of current. If you change the direction of current, they change their resistance. Some change their resistance because of temperature. Some change their resistance because of pressure. Some change their resistance because of intensity of light. Some change their resistance because of the moisture. Some change their resistance because of I think I have covered all physical things that are important. So yes, different things. I mean, like some change their resistance because of pressure, temperature, intensity of light, uh, direction of current, etc., etc. Now, these conductors who change their resistance because of because of change in physical condition around them, they are called thermistor. They are called semiconductors. Sorry, and thermistor is one of them. Thermistor is a kind of resistor whose resistance depends on temperature. These are negative coefficient thermistors. Negative coefficient thermistor means when you increase the temperature around the thermistor, or when you increase the temperature of the thermistor, resistance of that thermistor decreases. With the increase in temperature, resistance will decrease. So here we go. This is the graph of resistance and temperature. Excuse me. The resistance and temperature. When we increase temperature, resistance is decreasing. And this is not an inverse proportional relationship. Remember, it is a negative correlation. There is a negative correlation between resistance of a thermistor and temperature in degrees Celsius. So when we increase temperature, resistance decreases, and it is not an inverse proportional relationship, it is a negative correlation. Now, we have already discussed charge density, but I need this thing fresh in your head again. Charge density is number of free electrons or charge carriers per unit volume. Charge density is, number density is number of free electrons or number of charge particles which are responsible of transferring energy in a conductor divided by volume of the conductor. Now, today's lesson is about drift velocity. I told you electrons in a conductor, they're supposed to drift. Drift means if one electron enters the conductor, all the electrons of the conductor, they get a push forward and the last electron goes out. Such a movement is called drift. So here is a conductor. So what happens is, let's say I name this electron as this is an electron that I'm pushing in. Let's name this one. This is Joe. Okay, this electron is Joe. So what happens? All the electrons, there are so many electrons in the conductor. They will have a forward force, and the last electron will pop out. So what will happen is this Joe will get here. And then another electron will come in. So Joe will be pushed to the next position and next position. And the electrons are getting out as well. With any new electron coming in, one more electron is going out. So what will happen? All the electrons will be having a push in the forward direction. This kind of movement is called drift. So electrons drift, but I'm talking about this particular electron, Joe. Joe will definitely take some time, and there will be a time when Joe will actually come out from the other end. If this keeps on happening, I hope you understand. With every single electron coming in, Joe will get one seat next, one seat next, one seat next, and there will be a time when Joe will come out. If we know this length as L, we can and we know the speed with which it is moving, we can find out after how many seconds or millisecond or microsecond or any amount of second, after how many seconds this Joe, this Joe, it is not a person, it is name given to an electron. So if we know when this Joe comes out from the other end and we use that time and we use this length, we can find out drift velocity. But there is a small problem. It is not a big deal to find out the length of the conductor. You can just use a meter tape or a measuring tape or ruler or any device that can measure length to measure the length of that conductor. But the problem is the small problem I was talking about. That was sarcastic. Actually, how will we know when did the Joe came from the other end? How can we know when did the Joe came out? There, like we cannot see electrons, we cannot classify them, we cannot paint them, we cannot put a marker on them. That is not true at quantum level, but right now we are talking about AS physics. So we cannot label this electron, so we will never know when did this electron came out of the other end, because the electron is definitely getting a forward push with every new electron coming into the conductor. We want to know what is the speed of this conductor, and in order to do that, we need to find out how much time this one electron will take to come out of the other side. The problem is we cannot recognize an electron. Okay. But remember, you are studying physics. Smart people find a solution that is easy. Okay. So here is the solution. Current equals to charge divided by time. Current equals to charge divided by time. Like around 10 minutes ago, I told you that the charge equals to charge on each particle multiplied by number of particles. That should also make sense. It is very simple. Now, charge on each particle multiplied by number of charge particles should give you total charge. So here we go. There is something missing. Okay, here we go. Volume of the conductor. Let me put. I normally put boxes on things that are important, but I did not over here. I don't know why. There we go. Number of charge particle is N, capital N, where small n, remember small n is not number, it is number density. Volume equals to AL. So don't you think capital N equals to NAL, NAL, and because charge equals to charge particle into elementary charge, or in this case, Q, charge on each particle. So Q equals to A, L, N, Q. Confusion? So charge to A L N Q. I equals to charge divided by time, so it will be A L N Q over T. Oh, A L N Q over T. Hmm. What should be the speed of the charge particles in the conductor? Speed, which is known as drift velocity, should be L over T. Does anybody see an L over T here?
Yes.
So can I replace it with drift velocity?
Yes.
Here we go. So drift velocity multiplied by area, multiplied by charge density, multiplied by charge on each particle is equal to current. Can we use it to find drift velocity? Answer is yes, we can. And that is drift velocity equals to I over A N Q. Now, this means that if there is a smaller area, will be more speed of the charge particle. If there is a higher charge density, higher number density, the speed of electrons will be slow. Remember, in like if you have a very good conductor, then the speed of electrons inside should be least. They will they will be transferring electrons. They will be transferring energy with least speed of electrons. So part materials that have more number density, they will have lower speed. So what is Q? Q is charge on each particle. Sometimes we use E, sometimes we use Q. So why do I use both? Answer is because I am preparing you for the exam, and in exam, examiner can use any of them because there is no binding on him. So drift velocity is I over A and Q. Drift velocity is inversely proportional to area. Drift velocity is inversely proportional to charge density. It is also inversely proportional to charge on each particle. Current, on the other hand, is directly proportional to drift velocity. If you need more drift velocity, you transfer more current to the conductor. Excuse me. This is the case. If you gradually reduce the size of the cross-sectional area of the conductor, where there is a bigger area, the current will be slow. When cross-sectional area will be decreasing, speed of the charged particles will be increasing. And when current becomes constant again, over there, so speed will also become constant. Remember, current is same in all over the conductor. In the last part, electrons will be fastest. Because why is that? Answer is, in a conductor, if there is there are three portions of this conductor. Let's say this is A portion, this is B portion, there is C portion. If there are 100 electrons coming this way, how many will pass B? 100. How many will pass C? 100. If there is same charge particles that are passing there, and you have smaller cross-sectional area, so if area decreases, length must increase. So in 1 second, more particles will be passing. The particles at C will be passing with more speed, and particles at A will be passing with less speed. By particle, I mean electrons in this conductor. So remember this formula. If you need a screenshot or something, please take it down. Okay, I'm back. Okay, just 1 second. Some messages in the सर ये आप कल करवा चुके हैं, कल शुरू किया था, आज कंटिन्यू किया है. ओके, टेकन सर, व्हाट हैज बीन टेकन?
I was talking about screenshot, I think.
Okay, 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 okay. Now, as the cross-sectional area of the conductor decreases, speed of the charged particle increase to transfer the same amount of current. Listen, current has not changed. Current is same, but for same current, same charged particles have to move through. But if the cross-sectional area is decreasing, speed will increase, and this resembles a mechanical concept known as Bernoulli's theorem. A Bernoulli theorem is that when a path for a fluid decreases in a pipe, the speed of the fluid will increase, although the pressure and the volume of the fluid is same. And you must have experienced this thing. For example, if there is a pipe in a lawn, and you want to water the lawn, and you want to make the water go far away from the orifice of the pipe, so what you do is you put your thumb on the face of the pipe. That will reduce the cross-sectional area, and the speed of the water will increase. This speed has increased without increasing volume of water. The volume of water is still the same, but as you have put thumb in front of in front of the hose, so area decreases and speed increases. You have witnessed that thing in mechanical world, but the same applies to uh, electrical world as well. Smaller cross-sectional area means more drift velocity. Now, here are some very common symbols. How many of them do you know? Any symbol that seems new to you, please let me know. Look at them carefully.